Welcome to lecture series on digital electronics under EPG Pathshala. Today we are going to study different number system representations which are specifically used for storing the information in the binary form in the computer memory. We would be talking about fixed number and floating point numbers. Basically, when the information is stored in the computer, whether it is a number, character, text, video, image or graphics, these kind of information could be really converted into binary form and then stored into the memory. As far as the size of the information is concerned, whenever the information is recorded into the memory, usually we prefer either storing in 8-bit memory, 16-bit, 32-bit, 64-bit or 128-bit depending upon the requirement of the system. Storage is one aspect, whereas when we talk about processing the information further by a microprocessor or embedded system or a microcontroller, naturally we require some kind of processing algorithms. Whenever we talk about implementing the hardware for handling integers as well as real numbers, we need to incorporate the mechanism or hardware for that. We would be talking about how real numbers are handled by microprocessors. The traditional microprocessors, they are having capacity to process only the integers. But when we talk about processing the real numbers or numbers in a scientific notation form, we have to talk about floating point number systems. Specifically, new microprocessors or modern microprocessors or DSP systems, they are capable of processing not only the fixed point numbers, but they can even handle the floating point numbers. The advantage of fixed point representation is that it is the fastest for processing. So, we usually use DSP for handling such kind of numbers. Normally, we talk about addition, subtraction, division and multiplication for integers. The same thing can be used for floating point numbers as well. For such kind of representations, IEEE has suggested a new standard for representation of floating point numbers, IEEE 754. In this section, we will be talking about the advantages and disadvantages of fixed point as well as floating point numbers, then how the arithmetic can be carried out for unsigned and signed numbers, and then we will be talking about representation of these numbers for DSP systems as well as advanced microprocessors. Learning objectives of this module are as follows: to understand how the integers and fractional numbers are represented, to study the fixed point number representations. Similarly, let us learn about representation of floating point representations. In addition, we will discuss about the fixed and floating point arithmetic. Data today comes in different forms including numbers, text, audio, image and video. The computer industry uses the term multimedia to define information that contains numbers, text, images, audio and video. All data types are transformed into a uniform representation when they are stored in a computer and transformed back to their original form when retrieved. This universal representation is called a bit pattern or string of bits. A bit is the smallest unit of data that can be stored in a computer. If we need to store a bit pattern made of 16 bits, we need 16 electronic switches. A bit pattern with 8 bits is called a byte. Similarly, we can talk about nibble, byte, double byte, word, etc. All data forms in different forms including numbers, text, audio, image and video can be converted into binary information by a device known as encoder. It is obvious from this diagram is that the architecture of all encoders is similar. The input form of data is different, but the output is in the binary form. Their storage method is the same and are kept in the local memory separately. To occupy less memory space, data is normally compressed before being stored in the computer. A data must be changed to the binary system before being stored into computer memory. However, there are still two issues that need to be handled: how to store the sign of the number, and second, how to show the binary point. For storing sign of the binary, one bit is reserved at MSB position depending on whether it is sign magnitude representation, 1's complement representation, 2's complement representation. If the bit value is 0, meaning the number is positive, and 1 means a negative number. For storing the decimal point, computers use two different representations: fixed point representation and a floating point representation. The first is used to store a number as an integer without a fractional part. The second method is used to store the number as a real with a fractional part. In almost all computations, the numbers can be represented and processed either of the two categories, fixed point and floating point notations. These representations provide a format to be used for storage and processing. A fixed point number representation utilizes a fixed number of digits or bits before or after the radix point as shown here. The numbers are usually stored as a signed or unsigned integer. An integer is normally stored in the memory using fixed point representation. An integer can be thought of as a number in which position of the decimal point is fixed. Consider n-digit signed or unsigned integer. Then the position of the decimal point is fixed. The decimal point is usually assumed to be right of least significant digit. Integers are whole numbers without a fractional part. For example, 13 and -11 are integers, whereas 23.75 and -0.25 are not integers. An integer can be thought of as a number in which position of the decimal point is fixed. Integers can be represented in 8-bit, 16-bit, 32-bit or 64-bit formats. Let us consider the representation of binary number 0001101 in fixed point representation. In this case, the radix or binary point is assumed to the right of least significant bit. An unsigned integer is an integer that can never be negative and can take only 0 or positive values. Its range is between 0 and positive infinity, that is 0 to 2 raised to n minus 1. An input device stores an unsigned integer using the following steps. First, integer is changed to binary, and the second, if the number of bits is less than n, zeros are added to the left. Let us consider the storage of decimal 5 into 8-bit memory location using unsigned representation. 5 in decimal can be represented as 00000101 in binary. Note that decimal 5 requires only 3 bits, but for 8-bit memory storage 5 zeros are added before binary 5. So far, we have treated all of our numbers as unsigned or positive only. To implement signed integers or signed fractions, we need a mechanism to denote the sign itself, positive or negative. Unfortunately, this introduces a new problem. So we all need to see there are three different approaches, all of which add a special bit as the sign bit. If the sign bit is 0, number is positive. If the sign bit is 1, the number is negative. If we have 8-bit number, does this mean that we now need 9 bits to store it, with 1 bit used exclusively for the sign? And the answer is yes. The first signed integer format is sign magnitude method, where we add a bit to the front of our numbers that represents a sign. In 4-bit, the decimal number 3 is represented as 0011 and -3 is represented as 1011. Notice in 4 bits we can store 16 numbers in unsigned magnitude, that is from 0000 to 1111 or decimal 0 to 15. But in signed magnitude method we can only store 15 numbers between -7 and +7. So we lose a number. There are two problems in signed magnitude representations. First, 0 is now represented in two ways, 0000 and 100. So we lose ability to store an extra number since we have two zeros. Secondly, we cannot do ordinary arithmetic operations using signed magnitude. We have to trip off the sign bit before the operations and insert the sign bit on the answer. That requires extra hardware. Let us discuss the representation of signed integer representation using ones complement method. In this technique, the positive number remains the same. While representing negative numbers, all bits are inverted, that is, zeros become ones and ones becomes zeros. Let us represent +5 in 4 bits. It is 0101 and -5 is represented as 1010. It is interesting to note that first bit represents only sign bit, but also it is a part of a number. There is a problem in ones complement technique. In this case, 0 has two representations, 0000 and 1111. Hence, ones complement method is not recommended for arithmetic operations. Finally, let us discuss how twos complement method is used for representing signed numbers. The positive numbers remains the same and negative numbers, all bits are inverted, zeros becomes ones and ones becomes zeros, and add 1 to the result. Let us now see some examples. For example, +5 in 4 bits is represented as 0101 and -5 can be represented as 1010 plus 1, that is 1011. Note that first bit is not only a sign bit but also a part of a number. There are two advantages. First, there is only one representation for 0, 0000, and second, one additional number can be represented using twos complement method. Thus, the range of numbers under twos complement method in 4-bit is -8, that is 1000 to +7 0111. Hence, twos complement method is recommended for arithmetic operations. We have discussed the representations of signed or unsigned numbers in fixed point representations. The problem now is how to represent fractions with finite number of bits. Let us consider a 10-bit number represented as A1, A2, A3 dash 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 dash, say up to 18. Out of these 10 bits, rightmost 2 bits can be used for storing the fractions. In this representation, radix or binary point is assumed to be after a 8th bit. Note that binary point is not stored. It is possible to use fixed point representation for real numbers. The binary fractions can be stored by scaling the numbers so that binary point is positioned at some other location. For example, let us consider the representation of 4.73. The binary representation of the above decimal number is 0100.11, which is shown in the figure. This method assumes the decimal point is in a fixed position and it relies on using fixed number of bits for both integer and fractional parts. Let us consider another example of representing real numbers using fixed point representations. 10011.101. Integer and fractional parts are written separately along with their weights. Sum of weights results the integer and fractional parts. Here, sum of integers results in 19 and sum of fractional part gives 0.625. So, the real number represented by fixed point notations is 10011.101, that is 19.625. To summarize, radix point is assumed in fixed point. There are fixed number of bits for both integer as well as fractional part. Only bits are stored in memory. Binary point is shifted to the left by 2-bit positions, which are referred to as scaling. With scaling or shifting the fixed binary point, the fixed point representation allows the representation of numbers with fractional components as well. While interpreting the bits of the numbers stored in the memory, radix point can be repositioned by multiplying the stored number by a scaling factor. The scaling factor in binary is always 2 raised to fixed exponent. The scaling factor helps to reposition the radix point and allows us to represent integers as well as real numbers by fixed point notations. There are 3 methods for repositioning the radix point. The radix point is moved to the right or to the left or remains where it is based on the scaling factor. First, for scaling factor 2 raised to n, where n is equal to 0, that is 1. In this case, radix point is not moved and the numbers is stored at the same position. Second, for scaling factor 2 raised to n, that is n is equal to 1 or more, in such a case radix point is repositioned so that radix point is moved to the right. In this case, additional zeros are appended to the right of LSB. The actual number to be represented is larger than the binary number that was stored in memory. So, let us consider a binary number 00001011 is stored in memory using 8 bits of storage. If n is equal to 2, then the scaling factor is 2 raised to 2. As the scaling factor is greater than 1, we move the radix point 2 places to the right. This gives a binary number 00101100. For scaling factor 2 raised to n, where n is equal to -1 or more, in this case the radix point is repositioned so that radix point is moved to the left. In such a case, the number that is to be represented is smaller than the number that was stored. This method allows us to represent the fractional part. Let us consider the binary number 00001011 is stored in memory using 8 bits of storage. If n is equal to -2, then the scaling factor is 2 raised to -2. As the scaling factor is less than 1, we move the radix point to 2 places to the left. This gives a binary number 000010.11. From these three approaches, it is clear that shifting is the key for the representation of fixed point notations. Shifting an integer to the left by 1 bit position is equivalent to multiplying the number by 2. Shifting the integer to the right by 1 position is equivalent to dividing the number by 2. In these notations, decimal or binary point is fixed between two groups of bits. The decimal or binary point is never stored in fixed point formatted number. As the decimal point or binary point position is known and fixed, it is not necessary to store the decimal or binary point. This is also referred to as implied binary point. For representing numbers in fixed point notations, there are various methods used to represent radix or binary point and word length. For representing fractions under fixed point notations, Q format is normally preferred. Q indicates quality of fractional bits. The fractional number ranges from +1 and -1. In addition, F indicates number of fractional bits, S indicates number of sign bits, M indicates total number of integer bits. There are two Q formats. The first one is QF point. It is a format notations with F indicating number of fractional bits. For example, Q15 represents a number with 15 fractional bits. Second one is QM.F. It is a Q format notation with M indicating the number of integers and F indicating the number of fractional bits. So, for example, Q1.14 indicates 1 integer bit and 14 fractional bits. The QF notations provide ambiguous representation because it does not specify the word length. However, in many digital systems, word length is either 16 or 32 bit. The QM.F is unambiguous notation because the entire word is in 2's complement integer format and the sign bit is implied. Total number of bits are n is equal to m plus f plus 1 for signed numbers. So, for example, 16 bit number we can represent Q 2.13. It indicates 2 bits of integer and 30 bits for fractional part and 1 sign bit. Number of bits in the representation will decide the range of integers. In addition to the bit length for integers, it is important to know various representation schemes like signed and unsigned integers. The dynamic range and resolution of fixed point representation can be known as basic relation. An 8-bit unsigned integer can have dynamic range 0 to 255, whereas 8-bit signed integer has a dynamic range of -128 to +127. The dynamic range for 16-bit unsigned digital system is 0 to 2 raised to 16, that is 0 to 65,536, and for signed systems dynamic range is -32768 to 32767. The resolution of unsigned 8-bit system is 2 raised to -8, that is 1 upon 256. For signed 8-bit, the resolution is 2 raised to -7, that is 1 upon 128. The resolution of unsigned 16-bit number is 2 raised to -16, that is 1 upon 65,536, and for signed 16-bit number 2 raised to -15, that is 1 upon 32,768. Application areas. Fixed point notations are preferred for representing fractional values, usually in a microprocessor or a microcontroller where there is no floating point unit. In such case, fixed point notations provide improved performance and accuracy for given application. Most of the commercially available embedded systems and microcontrollers do not have FPU. There are few limitations of fixed point representations. The first one, it cannot be used for representation of very large numbers or very small fractions. To represent large numbers or very small numbers, we need a very long sequence of bits. This is because we have to give bits to both integer as well as fractional part. And third limitation is more number of bits are required to store large number or small fractions. So, let us now start the discussion on floating point representations. The first and the important question is, why do we need floating point? There are several reasons for it. Many numeric applications need numbers over a huge range, for example, nanoseconds to gigahertz. Second, most scientific applications require real number like pi, e, etc. But so far we have only have integers. So, what do? We could implement the fractions explicitly, for example, 1/2 1 upon 1024. Second, we could use bigger integers, for example 64-bit integers. Floating point numbers allow an arbitrary number of decimal places to the right of decimal point. These numbers are often represented in scientific notations. To represent the real numbers, the floating point notations normally employ scientific notations. In this case, the bits are used to represent mantissa, very few number of bits to represent exponent. Thus, we can have a standard scientific notations as plus minus mantissa into 10 raised to exponent. Similarly, floating point representations using scientific method for binary can have the form as shown below, plus minus mantissa into 2 raised to exponent. For example, plus 1.314275,462 into 10 raised to minus 23 or minus 5.0 into 10 raised to 73. When we deal with very large and very small numbers, we often resort to using scientific notations. Calculators, for example, often represent the results of large calculations this way, because there is an insufficient number of digits to show the result normally. So, let us consider a large number minus 123 and 14 zeros can be represented as minus 123 into 10 raised to 14. Here we have 4 parts: sign, mantissa, the base and the exponent. 123 is called the mantissa, 14 the number is the exponent, which is the number of places to move the decimal point. We can alternatively write the same number in different scientific notations as minus 12.3 into 10 raised to 15 or minus 1.23 into 10 raised to 16. Out of these, last notations is the normalized floating point representation. The term floating point is used for representation because there is no fixed number of digits before and after the radix point. The radix point can float. A number in scientific notations that has no leading zeros is called as normalized number, which is normally used for computer arithmetic. For example, 1.234 into 10 raised to 8, 12.34 into 10 raised to 7, 123.4 into 10 raised to 6, 0.1234 into 10 raised to 9. Out of these 4 examples of scientific notations, only first number is normalized notations and other three are not. Similarly, in binary, one can write the numbers in scientific notations as 1.00110011 into 2 raised to 8, 100.110011 into 2 raised to 6, 10011.0011 into 2 raised to 4, or 100.110.011 into 2 raised to 3. Out of these 4 examples, only first number is normalized scientific notation and other 3 are not. To keep the number in normalized form, it is necessary to have a base that we can increase or decrease by exactly the number of digits or bits. The number must be shifted to have one non-zero digit to the left of decimal point. To resolve the problem of synonymous form, a rule that the first digit of significand must be 1, usually it is hidden, which no ones to the left of the radix point. This process is called as normalization, results in unique pattern for each floating point number. In this simple model, all significants must have the form 1.xxxx into 2 raised to y. A standard scientific notations for floating point numbers in the normalized form provides 3 advantages. It simplifies exchange of data, also simplifies floating point arithmetic, and it increases accuracy of the numbers. Floating point numbers are used for all modern computing systems. Due to wide use of these numbers, the format for storing floating point numbers in memory is standardized by IEEE. The most important floating point representation is defined in IEEE standard 754, adopted in 1985 and revised in 2008. This standard was developed to facilitate the portability of programs from one processor to another and to encourage development of sophisticated numerically oriented programs. The standard has been widely adopted and used on virtually all contemporary processors and arithmetic coprocessors. IEEE 754 covers both binary and decimal floating point representations. It defines different ways to store represent binary numbers in memory. These are single precision, which utilizes 32 bits, double precision, which utilizes 64 bits, and extended precision, which utilizes 128 bits of storage. The 3 basic binary formats have bit lengths 32, 64 and 128 bits. We can represent floating point numbers with 3 binary fields, a sign bit S, an exponent field E and fraction field F. Exponent of 8, 11 and 15 bits respectively. The IEEE 754 standard defines several different precisions. A single precision numbers include 8-bit exponent field and a 23-bit fractions for total of 32 bits. Double precision numbers have an 11-bit exponent field and a 52-bit fraction for a total of 64 bits, whereas extended precision numbers have 15-bit exponent field and 112-bit fraction for a total 128 bits. But unlike integers, IEEE values are stored in sign magnitude format. The normalized floating point binary number can be represented as n is equal to -1 raised to s into 1 point fraction into 2 raised to exponent minus bias. There are 3 parts. S is a sign bit, 0 for non-negative and 1 for negative numbers. E exponent, the exponent is stored in bias representation, that is excess representation to permit both positive and negative exponents. To provide negative exponent, a bias exponent is used. A bias is a number that is approximately midway in the range of values expressible by exponent. Normalized significant. It is always given as 1.0 less than significant less than 2.0. We normalize the floating point number so that the decimal is implied to be before the first one bit, and in shifting the decimal point, significant is fraction with 1 point is stored. The significant is stored in unsigned magnitude. An IEEE 754 single precision number is divided into 3 parts. The IEEE has established a standard for floating point numbers. IEEE 754 single precision floating point standard and IEEE 754 double precision standard. In this standard, sign bit is B31 in a single bit precision and B63 for double precision. Exponent for single precision, the excess or bias 127 is used. Normally one expects the bias to be half the number of representations. Nevertheless, the excess is 127. Thus, the range of possible exponent is minus 127 less than or equal to exponent less than or equal to 128. In double precision, the bias is 1023. Fraction. Normally, you would represent the significant, also called as mantissa. This would mean representing d dot f f f f dot dot dot. However, recall that base 2 d is equal to 1. Since d is always 1, there is no need to represent the 1. You only need to represent the bits after the radix point. Thus, 1 left of radix point is not explicitly represented. We call this as hidden 1. Let us consider an example of floating point representation. Let n is equal to 0.75. It is represented as 0.11 in binary. In normalized form, it is represented as minus 1 raised to 0 multiplied by 1.1 into 2 raised to minus 1. In this, significant has 1 point is implied. The fraction in binary is 100.0023 bits. Exponent e minus 127 is equal to minus 1. Therefore, e is equal to 127 minus 1, that is equal to 126, and we can have its binary form, and s is equal to 0. Thus, we can represent the number as 0, 0, 1 1, 1 1, 1 1 0, 1 0 0 up to 23 bits, that is equivalent to 0, which is represented in hex 3f4 0 0 0 0 0. Normalized floating point numbers. In normalized form, the radix point is replaced by first non-zero digits 5.6789 into 10 raised to minus 15 or 1.00110 into 2 raised to 12. For binary number, leading bit is always 1, need not be represented explicitly, which provides an advantage that it saves 1 bit of storage. In IEEE 754 normalized single precision representation, n bit pattern has finite number of combinations. It is not possible to represent the infinite numbers in the real axis. This indicates not all floating point numbers can be accurately represented. Instead of, closest approximation is used, which may lead to loss of accuracy. The negative and positive smallest as well as largest numbers are indicated in the table. In single precision range, exponent 0 0 0 0, 0 0 0 0 and 1 1 1 1 1 1 1 1 are reserved. The smallest value of exponent is 0 0 0.000001. Actual exponent for this number is e minus 127, that is equal to 254 minus 127, that is equal to 127. The fractional part is 000 20 up to 23 bits and significant is 1.0. Thus, it represents a floating point number plus minus 1.0 into 2 raised to minus 126 or approximately plus minus 1.2 into 10 raised to minus 38. In single precision, the largest value of exponent is shown here. The actual exponent for this number is around 126. The fractional part is represented as shown here in 23-bit format and significant is around 2.0. Thus, it represents a floating point number plus minus 2.0 into 2 raised to plus 127, and you can have a decimal representation. In double precision, the range of exponent is you have 00000000000 total 11 bits and all 11 bits are reserved. The smallest value of exponent is 10 bit 0 and 1. Actual exponent for this number is around minus 1022. The fractional part is 000 almost 52 bits and significant is 1.0. Thus, it represents a number plus minus 1.0 into 2 raised to minus 1022, and that gives the decimal equivalent as plus minus 2.2 into 10 raised to minus 308. In double precision, the largest value of exponent is 10 bit 1s and a 0. Actual exponent for this number is around plus 1023. The fractional part is 111 52 bits and significant is around 2.0. Thus, it represents plus minus 2.0 into 2 raised to plus 1023. So, it is around plus minus 1.8 into 10 raised to plus 308. In the normalized floating point representation, what if the result is too large, that is greater than 2.0 into 2 raised to plus 128? Obviously, overflow will occur. Overflow occurs when exponent is larger than 8-bit exponent field. Similarly, in the normalized floating point representation, if the result is too small, that is greater than 0, but less than 1.0 into 2 raised to minus 127, obviously underflow will occur. Underflow occurs when negative exponent is larger than represented in 8-bit exponent field. Denormalized floating point numbers. Denormalized form can represent very small numbers close to 0 and 0, which cannot be represented in a normalized form as shown in the figure. If e is equal to 0, but the fraction is non-zero, then value is in the denormalized form and a leading bit of 0 is assumed. For a single precision, e is equal to 0 and the number is represented as shown here. Similarly, for double precision, e is equal to 0 and the number is represented as shown below. In denormalized notations, the floating point has no hidden 1, that is no implied 1. This allows floating point numbers to define numbers very close to 0, and to handle this special case, it is agreed in this case the sign, exponent and mantissa are set to 0. The minimum and maximum denormalized floating point numbers are shown below. There is a d minimum, which is around 2 raised to minus 149 in single precision, d max, which is around 1 minus 2 raised to minus 23 into 2 raised to minus 126 in single precision, d minimum around 2 raised to minus 1074 in double precision, and d max, which is equivalent to 1 minus 2 raised to minus 52 into 2 raised to minus 1022 in double precision. Under denormalized floating point representation, there are three special cases for 0, infinity and NaN. 0 cannot be represented in a normalized form. So, what we need to do is assume E is equal to 0 and F is equal to 0. There are two representations for 0, plus 0 with S is equal to 0 and minus 0 with S is equal to 1. Infinity, the value of plus infinity, for example 1 upon 0, and minus infinity, for example minus 1 upon 0, are represented with an exponent of all ones, that is E is equal to 255 for single precision and E is equal to 2047 for double precision. F is equal to 0 and S is equal to 0 for plus infinity and S is equal to 1 for minus infinity. Not a number, that is NaN. It denotes that number cannot be represented as real number, for example 0 upon 0. So, NaN is represented with exponent of all ones, that is E is equal to 255 for single precision and E is equal to 2047 for double precision and any non-zero fraction. The IEEE has established the standard for representing the floating point numbers. IEEE single precision floating point numbers requires 32-bit storage and double precision requires 64-bit storage. Out of the n bits, that is 32 or 64 bits for a single or double precision standard, 1 bit is reserved for sign bit. The number of bits for storing the exponent is 8 bits for single precision and 11 bits for double precision numbers. 23 bits and 52 bits of storage is required for storing the fraction part of a single precision and double precision numbers respectively. The exponent is stored in a bias representation, that is excess representation, to permit both positive and negative exponents. The floating point arithmetic IEEE standard use the following approaches: round to nearest, second round towards plus infinity, round towards minus infinity and round towards 0. For storing IEEE standard floating point numbers, following procedure needs to be followed. First, store the sign in either 0 or 1. Change the decimal number to binary. Third, normalize the floating point number. Fourth, find the values of E and M. And fifth, concatenate S, E and M. Let us take example to understand floating point representation. Interpret the given number, which is a bigger number. Here IEEE 754 indicates it is a 32-bit floating point representation pattern. Sign bit S is equal to 0, which is a positive number. E is equal to 10000000, that is 128 decimal. Fraction is 1.11 in binary and that is approximately equal to 1.75 in decimal. The number is plus 1.75 into 2 raised to 128 minus 127. So, that is equal to 3.5 in decimal. In this section, let us begin with the interesting part, that is floating point arithmetic. We can perform all basic arithmetic operations with floating point. Let us start with a floating point addition. The procedure is: first, rewrite the smaller number such that its exponent matches with the exponent of larger number. Step number 2, add the mantisas. Step number 3, normalize the sum and check for overflow or underflow. And last step, round the sum. So, this is about the floating point addition. Let us discuss floating point subtraction. Step number 0. First, the numbers are given. Step 1, significant of lesser exponent is shifted right until exponents match. Step number 2, add significants. Step number 3, normalize the numbers and check for any overflow or underflow, and step number 4, carry out the rounding. Floating point multiplication. The procedure is separate sign bit from the numbers. Step number 2, add exponents of both multiplicand and multiplier. Third, multiply the significants. Further, the result is normalized and rounded, checked for any overflow. Step 5, replace the sign bit by the sign of product. Floating point division. The procedure is step number 1, separate sign bits from the dividend and divisor. Step 2, check for zeros and infinity. Step 3, subtract exponents. Step 4, divide significants. Step 5, further the result is normalized and checked for overflow or underflow. Step 6, perform the rounding of the result, and last step, replace sign by the sign of quotient and write remainder. Let us now summarize the things that we have studied in this module. We have seen how the numbers are represented in the binary form. Usually, we prefer either fixed point notations or floating point representations. Fixed point notations are normally preferred to be stored in a Q format, whereas the floating point representations are normally stored using IEEE format. In IEEE format, there are 3 different representations. The first one is about the single precision, second is double precision, and the third one is extended precision. In all these cases, usually we store the sign bit, then we store the exponent, then significant. So, these are the 3 things those needs to be stored. While storing the exponent, we use the bias notation. Now, whenever these fixed or floating point numbers are to be used, we need to find out what are the application areas for these representations. Usually, for traditional microprocessors, there are no floating point units. So, naturally fixed point representations are normally preferred, and the way to represent is already discussed in this session. Whenever we go to the modern methods of processing, usually for embedded systems or DSP or a modern microprocessors, naturally we have to use both the representations which supports fixed point as well as floating point representations. So, the advantages of fixed point notations is that it is faster to process, whereas the floating point notations provides us the flexibility. Now, with these representations, I am sure that we can store the information depending upon the requirement, whether the number is very small to represent or very large to be represented. We will be restricting ourselves to scientific notations and IEEE format. Thank you.